2,200,000,000 tons of waste are generated across the globe every single year. Within this massive accumulation of refuse, paper products account for nearly 26% of the total volume, establishing paper as the most prevalent type of trash found on the planet. One can notice how this discarded material could theoretically cover millions of football fields if spread out across the landscape. But this is just the beginning. Why is the potential for reclamation so high in this specific industry? At first glance, a used sheet of paper seems like a single-use item destined for a landfill. But in reality, the cellulose fibers within the material possess a remarkable resilience, allowing them to be recycled up to 7 times before the structural integrity becomes unusable for production. Everything only gets more complicated as the raw waste arrives at the facility. Hundreds of tons of old, discarded paper enter the gates of one of the largest recycling plants in the United States every 24 hours to undergo a complete industrial rebirth. It is visible how the equipment gradually sorts through the chaotic piles of refuse to begin the transformation. The process is only gaining momentum within the facility walls. Automated systems and heavy conveyors move the material through various stages of purification and chemical breakdown. One can notice the steady mechanical rhythm as the facility works to turn mountains of scrap into smooth, bright white rolls of toilet paper designed for everyday use. This stage of the manufacturing cycle ensures that the discarded fibers are cleaned and pressed into a new form. The machinery operates ceaselessly to maintain the flow of the material through the refining tanks. From here, the transformation moves to the next phase of processing as the finished product is prepared for distribution. 500 tons of waste are sorted every single day at the processing facility. Why is such a massive volume of discarded material collected and categorized with such intensity? At first glance, the heaps of old invoices, discarded newspapers, and flattened cardboard boxes appear to have lost all functional value. But without this rigorous separation from plastics, metals, and glass, the raw fibers necessary for high-quality production would remain trapped within the refuse. Recycling trucks navigate local neighborhoods every morning to initiate the collection phase. One can notice how mechanical arms extend with hydraulic precision to grip the bins, lifting them toward the rear compartments of the vehicles. The process is only gaining momentum. Each movement is part of a coordinated logistical cycle designed to salvage every fragment of used paper from the community waste stream. It seems simple to just throw away old documents or packaging, but in reality, these materials represent the primary source for fresh industrial rolls. The convoy of trucks moves steadily toward the sorting plant, which serves as the central hub for the entire surrounding region. Here, the equipment gradually filters the incoming stream to ensure only paper fibers proceed. Automated systems and manual sorters work in tandem to isolate the paper from contaminants. It is visible how the piles of mixed waste are thinned out as they move along the belts, leaving behind only the organic fibers. This is not the limit of the purification. Everything only gets more complicated as the materials must be thoroughly cleaned and processed to remove inks and adhesives. Because this technology allows for the creation of bright white rolls, the demand for virgin timber is significantly reduced. This industrial transformation bypasses the need for felling trees, instead relying on the constant circulation of existing waste. One can notice the steady flow of sorted material being baled and prepared for the pulping stage. The paper is eventually transformed into fresh, uniform rolls that serve an essential purpose in daily domestic life. From a discarded scrap in a trash bin to a refined product, the journey follows a strictly managed technical path. The material leaves the sorting stage, transitioning into a calm phase where chemical and mechanical refining will soon take place. Thus, the waste reaches the standard ready for the further stage of its life cycle. 100 rolls of paper are consumed by a single person every 12 months on average. This massive volume of waste is rarely clean when it first arrives at the facility, as it is saturated with various industrial and organic impurities. One can notice how nylon fragments, shards of plastic, small metal scraps, and even organic food remnants are mixed into the mass. Why is such a thorough cleaning necessary before the paper can be repurposed? It only looks obvious that paper can be melted down immediately, but in reality, any foreign object will compromise the structural integrity of the final product. The raw waste is dumped onto a long conveyor belt that moves steadily toward the primary sorting zone. Manual labor remains the first line of defense against contamination. Waste workers stand along the line, their hands moving with rapid precision to extract large pieces of nylon and other non-paper materials. Because these individuals work in direct physical contact with the waste for the duration of their shifts, they are equipped with full protective gear, including face masks, thick rubber gloves, and impact-resistant safety goggles. This manual intervention ensures that only newspapers and printed sheets that remain clean enough for reuse continue down the line. But this is just the beginning. Mechanical systems take over once the largest contaminants are removed. The paper is fed into a vibrating material separator, a massive piece of equipment that serves as a primary mechanical filter. It is visible how the machine generates constant high-frequency vibrations across its surface. As the material spreads out, the lighter paper pieces migrate forward due to the oscillation, while heavier objects such as cardboard, thick plastic, or metal fragments fall through the openings below. The process is only gaining momentum. Airflows and light sensors provide a secondary layer of purification. The material stream enters a specialized air separator, where powerful wind currents intersect with advanced optical sensors. As the belt moves, the system scans the surface to identify lightweight non-paper objects like plastic bags, thin film wrappers, or soft packaging. In an instant, high-pressure air jets detonate with a short hiss, blowing these specific items off the line while the paper remains undisturbed. Everything only gets more complicated as technology advances. In some of the most sophisticated facilities, human intervention is replaced by automated robotics. These systems are equipped with high-resolution computer vision that allows robotic arms to identify waste based on shape, material density, and color. One can notice how the manipulators move with jewelry-like precision, picking up individual items and depositing them into designated bins. This cutting-edge technology allows the facility to process much larger volumes of waste while simultaneously increasing the purity of the sorted material. Shredding prepares the cleaned paper for its physical transformation. The selected sheets are fed into an industrial shredder where rows of rotating metal blades tear the material apart without pause. Each sheet is reduced to thin, uniform strips that fall into growing heaps on the floor. At first glance, this looks like the end of the sorting phase, but the material must still be prepared for transport. Transition to the next level. A bulldozer moves forward with a low hum of hydraulics, pushing the massive piles of shredded strips into a high-pressure pressing chamber. Inside, the paper is tightly compacted under several tons of force into neat, dense square blocks that resemble oversized recycled bricks. This compaction is essential for logistics, as it maximizes the weight that can be carried in a single load. A forklift then maneuvers into position, lifting the finished bales and stacking them onto trucks. The material leaves the facility, transitioning into a calm stage as it heads toward the factory for its final processing into toilet paper. 800 kilograms is the mass of a single compressed bale of shredded paper as it arrives at the processing facility. Why must these massive blocks undergo such a violent transformation inside a pulper? It would seem that simple mixing would suffice to break down the material. But without the intense mechanical action of a high-powered agitator, the dense cellulose fibers would remain clumped together, making it impossible to create a uniform sheet. One can notice how a heavy-duty forklift maneuvers with precision to deposit each bale into the raw materials receiving zone. The scale of production is immense, as a single bale of this weight contains enough fiber to generate over 10,000 individual rolls. Once the paper enters the factory, it is fed into the pulper, which serves as the primary engine of the breakdown process. But this is just the beginning. The equipment gradually fills massive tanks with a mixture of 1 part paper to 10 parts water. At the bottom of these vessels, an agitator rotates continuously at speeds ranging from 1,000 to 1,500 revolutions per minute. This motion creates a powerful vortex that physically shears the paper, separating the individual cellulose fibers from one another. Depending on the specific configuration of the system, a single pulper can process a batch weighing between 2 and 10 tons. It only looks obvious that water alone cleans the material, but in reality, specialized chemicals are essential at this stage. Dispersing agents and de-inking compounds are introduced into the swirling slurry to strip away residual printing inks, surface coatings, and synthetic adhesives. One can notice how the mixture becomes progressively finer as the agitation continues. As the fibers are fully liberated, they naturally begin to intertwine and form hydrogen bonds, creating the fundamental structural web of the new paper. Everything only gets more complicated as the liquid suspension transitions into a stable, uniform state. This chemical and mechanical refining phase lasts between 30 and 60 minutes, dictated by the raw material quality and the required density of the final product. After the pulping cycle is complete, the resulting slurry still consists of up to 95% water. The process is only gaining momentum. The camera glides along the dewatering system where the watery pulp is transferred to consolidate the material thickness. Here, the slurry passes through rotary drum machines equipped with large spinning metal cylinders. The pulp adheres to a fine mesh on the drum surface as it rotates, while gravity and centrifugal force pull excess water into a recovery system located below. A moist, inflexible layer of pulp begins to take shape, signaling the transition to the pressing stage. At first glance, the damp pulp looks fragile, but the pressing system provides the necessary mechanical integrity. The material is fed between giant steel rollers covered with a protective mesh, rotating in opposite directions under extreme hydraulic pressure. These rollers do not just define the width of the sheet, they forcefully squeeze out remaining moisture to flatten the material. The equipment gradually reduces the thickness of the layer until it reaches a standard of 15 to 20 microns. The pulp slowly begins to transform into a continuous uncut paper sheet as it moves at a precisely controlled operating speed. Even though the passage through the rollers lasts only a few seconds, it is the primary factor in determining the mechanical strength and durability of the finished roll. The process does not end at this stage. One can notice how the thin sheets move into a calendaring system where heavy rollers smooth the surface and enhance the natural shine of the fibers. From the calendars, the paper is wound onto massive reels with diameters exceeding 1 meter. Each of these industrial reels holds several thousand meters of continuous material. Once the winding is finished, specialized lifting equipment lowers the reel from the spindle, and a forklift carries it toward the cutting line. Why are the central cores made from recycled cardboard with such specific stiffness? The winding process generates significant inward pressure that would collapse a weak tube. These cores are manufactured by feeding long strips of cardboard into a spiral winding machine. The strips wrap around a solid steel rod, while a specialized adhesive bonds the layers into a rigid, hollow cylinder. Transition to the next level. The machine automatically feeds the long cardboard tubes into a cutting station equipped with a sharp rotating blade. It slices the tubes into uniform segments measuring between 9 and 11 centimeters in length, with a standard diameter of 4 centimeters. This precision ensures that the cores fit perfectly onto the paper winding molds without any mechanical misalignment. The machine's accuracy prevents jams and ensures the paper rolls smoothly during high-speed production. The process is only gaining momentum as the giant paper rolls are sliced into narrower strips and aligned with the core winding line. Hollow cardboard tubes are mounted onto a high-speed rotating shaft capable of spinning at 3,000 revolutions per minute. This extreme velocity allows each layer of paper to stack with perfect symmetry. When the roll reaches its programmed length, the system executes an automatic cut and deposits the finished product onto a conveyor belt. It is visible how the machine applies a final droplet of adhesive to secure the end of the paper tail against the roll. This prevents the material from unrolling during the rapid movements of the transport system. Long, uncut logs of paper are arranged in perfect order on the conveyor, waiting for the final dimensional adjustment. Seen from a distance, the white rolls form a meticulously aligned sequence. The rolls are then transferred to an intermediate storage area via a stepped ramp conveyor. Each unit rolls into its designated position with a rhythmic motion controlled by advanced sensors and an intelligent sorting system. This area is not merely for holding. It acts as a buffer that regulates the pace between the high-speed winding and the subsequent packaging stages. Everything only gets more complicated as the final cutting begins. The long logs are fed into a high-speed cutting machine where an ultra-sharp blade spins at thousands of revolutions per minute. The blade slices the continuous logs into individual rolls with exact standard dimensions. Precision compression systems hold the paper in place during the cut, to prevent any fraying or distortion of the edges. After the cut, the round blocks move continuously along a high-speed belt toward the wrapping station. The equipment gradually unrolls a transparent plastic film from a large industrial spool to begin the packaging phase. This film is cut to size and wrapped around packs of 6 rolls with millimeter-level accuracy. The wrapped units then enter a heat sealing machine. Here, controlled thermal energy presses the edges of the plastic together to form a hermetic and durable seal. This thermal bond protects the paper from environmental factors such as moisture, dust, and bacteria during long-term storage. Finally, automated robotic arms utilize vacuum or mechanical grippers to lift each pack. They place the packs onto large pallets according to a pre-programmed stacking pattern that maximizes stability and space. The robots ensure that every pallet is perfectly balanced before it is transported to the loading docks for national distribution. The material is ready to move to the next processing phase without haste. 80 billion rolls of toilet paper are consumed across the globe every single year. Why does such a seemingly minor household item require such a massive industrial scale of production? At first glance, a single roll appears insignificant, but the manufacturing journey begins deep within natural ecosystems where massive timber stands are harvested. Wood remains the primary structural foundation for this material, serving as the essential raw source for every sheet produced. The process of transformation begins with the felling of towering trunks within vast forest tracts. One can notice how heavy machinery strips the bark and reduces the solid wood into a soft, fibrous pulp through intensive grinding and chemical breakdown. But this is just the beginning. The equipment gradually refines this organic mass, shaping it into incredibly thin sheets that are eventually wound into the cylindrical form found in every home. 400 rolls are used by a typical family of 4 over the course of 12 months, meaning each individual person consumes roughly 100 rolls annually. This massive demand places a relentless strain on the environment. 15 million hectares of forest are consumed by the global paper industry every single year to maintain this supply chain. This staggering loss of land is equivalent to nearly 1/5 of the entire Amazon rainforest, the vast territory often referred to as the Great Green Lung of the planet. It seems simple to discard a single-use product, but in reality, toilet paper ranks among the most heavily utilized and resource-intensive commodities in the entire paper sector. It does not end at this stage. Fortunately, another way forward has been discovered to mitigate this environmental impact. New methods aim to reduce the ecological footprint without forcing a sacrifice in the tactile comfort to which everyone is accustomed. The process is only gaining momentum as alternative fibers and recycled materials are integrated into the production line. One can notice how the industry is shifting its mechanical focus toward more sustainable inputs. The transition toward these new materials marks a definitive shift in the manufacturing cycle. From here, the transformation moves to the next phase of processing. 100% of the discarded paper fibers have completed their transformation from what seemed like worthless waste into functional household products. Why is such a complex technological cycle necessary for a commodity that appears so simple? At first glance, the transition from raw scrap to a finished roll looks like a basic mechanical reduction, but in reality, it involves high-pressure thermal processing and chemical purification to ensure the material is reborn as soft white toilet paper. The equipment gradually winds the massive paper webs onto cardboard cores at high speeds. One can notice how the tension remains perfectly uniform across the entire width of the machine to prevent tearing. But this is just the beginning. Slitter blades rotate ceaselessly to divide the wide master rolls into the standard widths found in nearly every household. It is visible how the mechanical arms move with millisecond precision to package the finished cylinders in protective polymer film. Everything only gets more complicated when the logistics systems take over to move the pallets. This concludes the surprising journey of fiber through the multiple stages of industrial sorting, shredding, and recycling. Thus, the material reaches the final standard and is ready to move to the distribution phase without haste.